Okay, this video is for Chapter 10 of Cutnell and Johnson, which deals with simple harmonic motion. So, simple harmonic motion is SHM. And there are four equations on the AP test and in your AP equation packet that relate to this chapter. Okay. So the two labs that we did that related to this chapter were Hooke's Law, which is where we put masses on a spring and measured how much the spring stretched. So from that lab, from that investigation, we were able to determine if we were to, looking at our mass, we had the force of gravity down. And it was balanced by a spring force up. And we were able to tell that as we added more weight, as we added more mass, this gravitational force increased, making the spring stretch, which means that the spring force is proportional to the stretch. And as you graphed that, you saw a linear relationship. Now the equation that goes with this, so we can calculate the force of a spring is equal to negative kx. Now, the k is the spring constant. It's a physical property of the spring. So how stretchy or how stiff is a spring, or the spring material. X is the amount that the spring has been stretched or compressed. This negative sign is to tell us that the force is a restoring force. So if you take, so I'm going to use my stylus here. So if the stylus was my spring, and if I stretch it, so the amount that I stretch it is x. And if I call stretching a positive direction, that means the force is acting in the negative direction. The force is trying to bring the spring back to its original size. But if I were to compress it and push it in, again, the amount that it's been pressed in or compressed is x. But now, x is a negative direction, and the spring is going to be pushing to the right, the positive direction, trying to get back to this normal length. So that's where that negative sign comes in. It's because it's restoring. It's trying to get back to the original. So the sign of x, whether x is positive or negative, is going to determine the direction of the force. Okay. So that's one equation. Okay. From that lab, we also talked about, you could think about the amount of energy that's stored. Okay. So if you think about a pinball machine, you've got a mass, which is the pinball, and you put it on the plunger, pull the plunger back, which means you're compressing the spring, storing energy in the spring. If you release, so think about force times distance, that distance is x. That force of the spring is going to be doing work. And the work that's going to be done is, if we were to release the spring and let it go, and it goes back to its normal dimensions, it will have been compressed x okay, so that's the distance x. And we can calculate the amount of energy in a spring, and it's going to be potential energy. So I always say potential energy is PE, S, so potential energy of a spring. Your equation packet is going to say that this is U, S, so U is potential energy of a spring. And the potential energy of a spring is going to be 1/2 times the spring constant times the square of the distance of stretch or compression. And this equation can use for any ideal spring. So if we were to compress this spring a distance x and then release it, we're storing potential energy, and then when we release it, this block is going to leave the spring and the block is going to gain kinetic energy. So we'll see a lot of problems where we can transform energy from spring potential to kinetic, and if we were to launch this block up into the air, it would go from spring potential to kinetic to gravitational potential as it moves up. Okay, so that is the second equation, and that relates to the chapter that we just finished dealing with work and energy. Okay, the final two equations that we have deal with the period Sorry, my computer froze there. So period. And period is a capital T. So the unit that we use for the variable, or the variable that we use, is a capital T. So we can find the period of oscillation. So you saw in the lab that as I stretched that spring and then let it go, that mass oscillated. It went up and down. And it kept going up and down. And if it was an ideal situation and there was no friction involved, no air resistance, it would go forever. You also saw that as I pulled the pendulum back and released it, the pendulum swung back and forth. So we can measure the period. Now, period is units of seconds, so it's a measurement of time. And it's how much time does it take for one oscillation to go back and forth, okay? So for a pendulum, pendulum's going to swing. So it'll swing this way and come back. So how much time does it take to get back to the starting point? For spring, it's going to go up and down. So if we stretch it or compress it, doesn't matter which way. So if we stretch it down, it's going to bounce up and then come back down. So how much time does it take to go up and come back to its starting point? So the two equations for this are given to you in the equation packet. The period of a pendulum is equal to 2 pi times the square root of L over G. And L is the length of the string. And you saw in the lab that the only thing that affected the period was the length of the string. The mass didn't affect it. The angle didn't really affect it. Angle does affect, if we were to truly look at this, and if you were to look at the book, angle does have an effect, but what we do is we call this the small angle approximation. So for small angles, the period of a pendulum directly obeys this equation. So this is the equation that we're going to use. as the angles get big, we add in more information, more variables. The math gets a lot more complicated. So for us, we're going to assume that it's for small angles, and this equation is going to work out. So 2 pi L over g, and g is the acceleration due to gravity. So meter per second squared. Length is in meter, so the units of meters cancel out. So we have the square root of some second squared, which is seconds. So that's perfect for the units. Now, for the period of a spring that's undergoing simple harmonic motion is again 2 pi. And 2 pi, because it's oscillating. So if you think about 2 pi is one complete revolution of a circle. So if you think radians, it's 2 pi is a circle. That's why this 2 pi is in here. Okay. So it's 2 pi times the mass divided by k, our spring constant. Now if we were to go back and look at this force equation, where the spring constant times a distance is equal to a force, so that means k has units of a Newton over a meter. Okay. So remember, Newton is a kilogram meter per second squared. So if we have a kilogram meter per second squared, I'm going to do that unit analysis on the other side here. So we've got a kilogram divided by a kilogram meter per second squared. And remember, I just said that k was a Newton over a meter. So meter here, my meters cancel out, kilograms cancel out, and I get 1 over, so square root of s squared, seconds. So the period, the units are working out there too. Okay. Final equation that relates is the frequency. And frequency and period are inverse of each other. So the frequency is measured in hertz, and a hertz is just an inverse second. So 1 over a second is equal to a hertz. So frequency is 1 over the period is 1 over the frequency. These go back and forth. They're just inversely related. Okay, so that's it for Chapter 10. There's a lot of stuff in Chapter 10 about angular momentum, and you see omega in there. We're going to deal with that when we talk about circular motion, so we will discuss that in the next section. I will see you after break. Enjoy the last few days of your break, and I will see you on the 6th.